Welcome back. We are now on this problem solving in the section of work, energy and power, just to showcase how a problem could be entertained in this section. It's not a difficult section, but you just need to tighten some screws here and there, especially on the approach, which is very crucial. In this case, we are given this question number 5 in a normal question paper. It's work, energy and power, and we're given this question to say a 70 kilogram box is initially at rest at the bottom of the rough plane, inclined at an angle of 30 degrees to the horizontal. Underline the word initial. That will help you a great deal. Just write VI equals to 0 there. So the box is pulled up the plane by means of a light inextensible rope held parallel to the plane. As shown in the diagram, the force applied onto the rope is 700 Newton, as in the diagram. 5.1. They're telling us to say, what is the name given to the force in the rope? The moment you see a rope, a cable or string, that the force that will be found there is a tension, fine, which is a non-conservative force. Next question, they say, give a reason why mechanical energy of the system will not be conserved as the box is pulled up the plane. Now, the obvious answer here would be mechanical energy won't be conserved because there is friction. Where there is friction, the mechanical energy is not conserved, or the system is not isolated, not an isolated system. That will be the options. And you can accept when the linear system is not isolated because there's friction, or the internal energy increases because of friction. Fine. The next one, the box is pulled up over a distance of 4 meters along the plane. The kinetic frictional force between the box and the plane is 178.22 Newton. Draw a free body diagram for the box as it moves up the plane. In this case, free body diagram will have various options. Up the plane, there's a pulling force, which is the tension, or you can just write 700 newtons, and there is a normal force. There will be the frictional force and the weight. This is easy. Normally they say start with the weight because all free body diagram has got the weight. Alternatively, the learner can write instead of the weight being this, they start with the components of the weight, Fg perpendicular and Fg parallel. And then because there's another force here which is friction, and we want them to be parallel, this would be friction. And then up the incline is still the tension, and this way in line with Fg perpendicular is the normal. So it's either this way or this way. You can see, if you want to analyze, you can even tell no work done, work is done, work is done, work is done. So there are 3 forces that are doing work on the object here. Same thing this side, tension is doing work, this is doing work, this is doing work. Tension doing positive work, the two are doing negative work. Therefore, with the tension, we'll talk about cosine of 0 degrees, and with Fk and Fg parallel, we'll talk about the cosine of 180 degrees. Just to anticipate what might come. Then calculate the work done on the box by the frictional force over 400 meters. So calculate the work done by friction. So in this case, we know that friction is doing work, yes, but can we calculate the work done by that friction? Of course, yes. So the friction is given in the statement. They are telling us to say the kinetic frictional force is 178.22. Therefore, we just say we know the formula of work done by a single force This is, you copy the formula from the formula sheet. This force is friction, 178.22, multiplied by 4 meters, and multiplied by, we said friction is doing negative work. It will be cosine of 180 degrees. Then from here, the answer, if you use your calculator, it must give you 712.88 joules. This should be negative. So, because friction is doing negative work, you get 3 marks for doing that. Next question, according to this, they say calculate, that is 5.5. Use energy principle to calculate the speed of the box after it has moved 4 meters. What is the final velocity there? Using energy principle. So you can use work done by non-conservative force, or you can use work energy theorem. So let's go the easiest one. Fine. Work energy theorem says work net equals to delta EK. Therefore, which forces are doing work here? There are 3 in this case. There's a work done by friction, we just calculated. There's a work done by the tension, plus work done by the gravitational force here. Work done by gravitational force, you can say, then which will be your half mvf squared minus half mvi squared. Thanks. This one we just calculated is minus 712.88 plus work done by tension. We can calculate. We know the tension is 700, therefore we'll have 700 for the force. 700 delta x is 4. Tension is doing positive work. I will have cosine of 0 degrees. And then plus work done by gravity, which is now in this case mgh cos theta. Height is not given. I can use fg parallel this one. Mg, what is fg parallel? Mg sin theta, don't forget. This is mg sin theta. Therefore, open the bracket, we'll have mass of the box is 70 multiplied by 9.8, multiplied by the sine of the angle with the horizontal is 30. This is the force, delta x is 4, multiplied by 4, and also multiply now by cosine of 180. This will be the expression on the left hand side, equals to the sine. The final velocity is the one we're calculating. We'll just substitute the mass, Vf squared minus half of 70. This is 0. Why do I struggle? Just write 0 because it starts from rest. If you use your calculator in all these calculations, then you will end up with the answer now. The answer will be the final velocity after 4 meters. It will be 4,52 meters per second. You can verify that one with your calculator as long as you have substituted all this correctly. Then you will get it right. I think that's the first. The second one, the last question here, which is your 5.6. They said to us, when the box is 4 meters up the incline, the rope accidentally breaks, causing the box to slide back down the bottom of the incline. What will be the total work done by friction when the box moves up and then down the bottom of the incline now? So they are just asking, in this case, to now, what will be the total work done by friction? In both cases, remember, friction will do the same work, but in opposite direction. So the total work, remember work is a scalar, then you just tell the examiner, it will be 2 times the work done by friction will be 712 negative 0.88. So it's unlike the vectors. If it was a vector, it will cancel out. Here now we talk about energy. So work is energy, then it will be now negative 1425.76. It will be 2 times 712, which is the work done by friction. We did it here. This is the answer, work done by friction. Therefore, that work when it's going up will do the same work when it's going down. So the total work done will be the sum of the two, which is this one. So I hope now at least it's opened up. You know the importance of free body diagram, and also knowing which force is doing positive work and which one is doing negative work. Very crucial in this section. And please know that whereby you can use work energy theorem. Remember also you can solve this problem using the work done by non-conservative forces. This will be the case. You can do it this way. You will find that now they will give you the same answer. Non-conservative forces in this case will be tension and friction. So those will be the case. Otherwise, we'll do some more questions on this one so that we can clarify and make sure that people now they see this section of work energy and power in a different light. It's not a difficult section, but it just needs interpretation. Thanks a lot. Bye.